Now we learned about binary heaps. And we mentioned that unlike a binary search tree, there's no order from left to right. This 33 and 77, we can swap them and it'll still be a binary heap. The beauty of binary heaps is that they take up the least amount of space possible because it's always left to right insertion, as we just saw. So there's no concept of an unbalanced binary heap. We don't have to rebalance it like a binary search tree. Because of this, because they do left to right insertion, as we saw in the previous video, they preserve this order of insertion, which is pretty amazing, right? And you can actually implement binary heaps using arrays versus what we did before with binary search trees where we used nodes. So the only guarantee that binary heap gives us is what I mentioned. The parent is always greater than the children. Now, besides being memory efficient and just compact because it's always a complete binary tree, binary heaps are really, really useful for things such as priority queues. And you might be asking yourself, priority queue, didn't we just learn about queues and isn't that the same data structure? Well, no. Because with queues, we just assume that it was first in, first out. You were the first person in line, you should get to go first into the roller coaster or the movies. Priority queue is something different. It is a type of data where each element has a priority. And elements with a higher priority are served before elements with lower priorities. You can think of this as a club. Let's say we have a nightclub that is very, very popular and there's a long lineup. And we let some people in. Everybody's happy. But then all of a sudden, we have some VIPs that showed up. Well, they pay a lot more money than the other customers, so we're going to let them in first. So now we have a different priority where even though they arrived later, they get to go in. They have higher priority. Another good example is an emergency room. You want to treat the patients that have the most severe symptoms or conditions, right? Another way to think about it is, let's say we're lining up to get into an airplane. We have the first person coming in, lining up, and then all of a sudden the captain shows up. And because the captain should get on the airplane before a normal passenger, the captain gets now put as priority, as the root node, because the value is higher, or at least in this case, the value is higher than the passenger. So let's say another passenger comes on. Because we're doing left to right insertion, we put the passenger to the right. So now we know we're going to let the captain go in, then the first passenger, then the second passenger. Next, we have a stewardess that came in. He or she should get to go before the passengers, but not before the captain. Well, in that case, once again, we place the stewardess below the captain, but to the right or to the left of the passenger. And then we have another passenger that comes. We do left to right insertion. We see a right spot down here, so we place them down here. So we see how everything gets balanced, which is nice, but it's also really, really easy for us to now let people into the airplane because we know the order. We go from the top, then left, then right, then left, then right, left, right, and we just keep going, keep going, keep going. We know the priority very easily. I'm sure you see where this might be useful in a lot of situations. To review, we learned what binary search trees are. They're great, but sometimes binary heaps or priority queues are even better. Although searching through a binary heap is a lot slower than a binary search tree, you have an idea of priority because insertion is done in order. So you know who should be first, who should be second, who should be third. And although we might have to bubble up inserts every once in a while if there's somebody that has really high priority, most of the time you get really fast inserts with binary heaps. And as we mentioned, lookups are slow, But you want to use binary heaps when you're just interested in finding the max or finding the minimum if it's a min heap. And a lot of the times in binary heaps and priority queues, you have a method called find max or find min that is O of 1, because you know right away that the top root node is the max or the minimum. So for those operations, it's really, really fast and great. And there you have it. I'll see you in the next video. Bye-bye.